Hi everyone, I'm Elviro, and this is Advanced Swift Optics. This is the menu. We're going to talk about functional programming. Now, who's excited about functional programming in Swift? Almost everyone. That's really good. I'm really happy. Let's see if we can convince the other guys. I mean, if you're here, you're probably interested, I guess. So, we're going to talk about functional programming, but in particular, the value of using data structures in precise data structures when we program. And then we are going to switch to functional optics, which is basically something that allows us to do sane data manipulation. And a word of caution, there's going to be a lot of code in these slides. I'm sorry, but you have to show the code to make to kind of demonstrate that these things make sense. But I have a repo on GitHub where there is this entire presentation and also a Swift playground where you can find all the code, compiled, etc. And I will provide the link at the end of the talk. So functional programming. Functional programming is one of those draw the owl problems where you kind of start using functions and then somehow you write the application without really knowing what you're doing. And I have to say that if you're like me and sometimes even programming in a functional way, I guess, for a long time, you sometimes get confused. I like to go back to the basics. I really like to go to this tweet by John DeGoes that says that functional programming is about programming with functions, of course, but the function that we care about have these three characteristics. They are total, so they do not crash. They accept every instance of the input types that we provide, and so they return an output for every input. They are deterministic, so they will return the same output. They do not access some, global shared mutable state, and they are pure. So basically, their only effect is compute the output. So they do not do side effects. And the rest is just composition, he says. But these three things are really important because there is no one functional programming in the world. There are different communities for different languages. And they use different tools and different abstractions. But every community, every way of doing functional programming is basically based on these three things. One of the main things that they always talk about is the pure part, which means we don't want side effects in our functions. But unfortunately, side effects are those things that actually make our programs do something useful. So how can we do this? Well, the point is using the appropriate tools, you can be as pure as you like. But there are patterns that we can use to actually employ some functional programming inside our apps. I really like the approach that was described by Gary Bernat in his classic talk, Boundaries, in which he says that a thing that we can do is that we can split our app, our software, into modules that have a core that is pure and functional, testable, readable, and then a boundary where everything that is effectful happens. At the boundary, we are connected and we talk with the other parts of the application or the outside world. So, pure function. Pure functions can only transform data, so they get data in and data out. As I said, I am not particularly interested in this talk about the fact that we don't want side effects. We have tools, for example, monads are used for this reason. No, I'm mostly interested in the first point, the fact that those functions must be total. Because for functions to be total, to accept every instance of an input type, we need to carefully devise our inputs. The inputs of a function are one or more instances of some types, and the outputs are the same, of course. One or more, of course, in Swift we can do this, okay? We can return more things. We have these very lightweight tuples that are very, very nice to use. This means that the data involved in our functions is as important as the function themselves. Actually, it's even more important. I really like this quote from Fred Brooks in The Mythical Man Month, which is a book from 1975, which says, show me your flowcharts and conceal your tables, and I shall continue to be mystified. Show me your tables, and I won't usually need your flowcharts. They'll be obvious. Flowcharts here is logic. It's saying, show me the logic, show me the implementation, but conceal your data, your tables, and I shall continue to be mystified. But if you just show me the data, and of course data that was carefully structured, I won't need your flowchart. I won't need to read your code. The data, the logic, okay, will be obvious from the data types. So creating appropriate data types is key to employing this approach in programming. Of course, the data structure that we want are immutable. By immutable in programming, I mean if I'm passing around a pointer to some space in memory, and the information stored in that space in memory is going to change over time when the pointer is still referenced, well, that data is mutable, and we don't want that. The problem is, of course, that at a certain line in code, that data could be of a certain type, they could contain some information, but after a few lines of code, the data could have changed. So this is not what we want, because information actually is immutable. Information doesn't change. What we do is we generate new information, and we make the old one, render the old one obsolete. So we would like to represent this idea, represent the fact that if I give you some information, that information is not going to change over time. And luckily, Swift gives us exactly the tools to represent this. We have value types in Swift. Value types, like structs and enums, have exactly this semantics. It's called copy semantics. Because if I have a struct, even if it's mutable because it has variable properties, and I give you that struct, and you change the struct, my struct is unaffected. So struct and enums are value types, have this kind of semantics, and they can be employed to do a lot of things. Classic thing is domain modeling. Okay, we can describe our entities with structs or enums, but also UI modeling. View models, for example, can be done with struct. We can describe the UI of our application, whatever is the pattern that you're using. I'm not talking about functional reactive programming here at all. Actually, I'm not talking about Swift, iOS at all. I am only talking about Swift. The thing that I'm talking about is not strictly related to iOS, can be used in Swift on every platform. So modeling of the UI with the structs, with these value types. So I can describe the state of my UI without using the UI classes, so I can make everything more testable. Transitional information. So information that has to pass from one context to another. So blobs of information that I can give a name to, a structure to, a clear, a precise structure to, and they are passed from one context to another. And also intent representation, because sometimes I don't really even need to use logic in my function. I can describe what the function is supposed to do using data. Here's an example. I have this function here, trigger action, that takes some data, and also takes this dependency, a listener. So what I'm going to do in this function is, given the data, given some state of the application, I'm going to call methods on this listener that was probably injected as a dependency somewhere. But I can do a different thing. I can actually create a data type that is called action result, an enum. So I describe the various options, the various possibilities, and I return this type from my function without passing my dependency. So I'm describing what the app is supposed to do, the intent, okay, of this logic through a data type. Another option, another interesting thing that we could do is we can transform things that were usually described as logic into data. For example, the fact that an int is positive, okay, is traditionally logic. Maybe we can put it in an if int greater than or equal to 0. But is positive can be seen also as a property of an int. Actually, a property with both a get and a set. From the outside, we can render this idea that an integer is positive like a property on a data structure, that it's also mutable in this case. So it possibly becomes an integral property of the int type. So data structures bring us joy because they allow us to separate the representation from the interpretation. That function example that I just shown is exactly this. I am representing my intent and my logic somewhere in a place at the core of my application, at the core of my module, where I want everything testable, clear, and precise. And then I will interpret this operation, this event, this action somewhere else at the boundary of my system. And I would say that structuring my application by using these data structures will make everything more readable, testable, and maintainable. Readable because I have nominal data types that describe things. I can read the code and I see, okay, this is the data type. This is what I expect. This is the state of the application that I'm expecting at this moment. I can make everything super testable because, of course, pure functions are the most testable thing out there. They're just data in, data out. I can test it by providing data and checking if the data that spits out conforms to my business logic. And also maintainable over time, because when I go back to the code like 6 months from now, I can read the code, understanding and not expecting something funny to happen on the background, okay? Because my functions will just return some data. And this is, of course, not just for functional programming. We can employ these kind of techniques. We can describe our logic with data types in any style. This is not really strictly related to functional programming, but because in functional programming we try to program with pure function for as long as possible, as much as possible, of course data structures will become crucial, okay, in our programming life. So data structures bring us joy, but also pain, because they can get messy and complex. Because if I really want to describe, for example, the state of the application at a certain point in time, and the application is complex, probably the data structure that we describe that will be complex as well. But I am using the complex word here very carefully, because the fact that the data structure is complex is not a problem of the data structure, it's a problem of my domain. The data structure is complex just because my problem is complex. And what the data structure is doing is exposing the complexity in the most explicit way. So I'm being very, very explicit. I'm showing off the complexity on the domain. I'm not hiding it. And I don't want to hide it. Because if I hide it and I go back to my code 6 months from now, I won't see the complexity is there and I will make mistakes. I can have lots of nesting in these data structures because, for example, when I try, I don't know, to represent the state of a part of the application, probably there will be a lot of things in that state. So I could have a data structure with a lot of data structure nested and a lot of types nested within types. And that it's very hard to manage. And also, usually, we like to operate on tiny parts. Maybe, for example, a certain event in our application has to trigger, okay, a mutation somewhere. We would like to mutate the state in a certain place. But just that, we would like to just operate on that tiny bit. But eventually, we would like to get a transformation on the whole state. And that's where optics come in. So optics are really tools to operate on data structure in an easier way. There are types, so usually structs. And the idea of optics is that they encapsulate relationships between data structures. In particular, they are called optics because the main metaphor for them is one of focusing. I'd like to focus on a part of a data structure. A part at any level of nesting, really, inside, a tiny part inside a data structure. I want to operate there, but then I want to lift the operation on that part on the entire data structure. Another way of seeing this metaphor is like seeing data from a different point of view. I also read this somewhere. It seemed cool. Now, an author naming. As I told you, there are different communities within the functional programming world. And actually, I would say that Swift is still trying to find its identity in the functional programming community. There are some people that support functional programming in Swift a lot with libraries, tools, specifications, etc. But there is still no clear way to do one perfect way to do functional programming in Swift, I would say. There are a lot of sources, and naming is an important element here, because if I'm talking about optics here, and you read an article on Haskell, for example, where they also talk about optics, you would expect to find exactly the same names for the same things. I've used two sources for the names in this talk. This article here, this is an academic article from 2009, I think, Profunctor Optics from Jeremy Gibbons, Matthew Pickering, Nicolas Wu, and this GitHub repository. Notice that they both say Profunctor Optics, but we are not caring about the Profunctor part here. I have the reference at the footer. So an optic, as I said, is a type, is a generic type. It has two parameters. Actually, this is like a KeyPath. I'm calling the parameters the root, that is the whole data structure, and the value, which is the part I am focusing into. And the KeyPath in Swift, which is something that we have in Swift, is very, very similar, same to generic parameters. This is not a coincidence, as we will see. I have to say that this is a simplified representation. Maybe some of you already read something about optics, or will read something this evening. In many representation, you actually see 4 generic parameters, 2 more, because we also could represent a generic change on both root and value. So I have 2 roots and 2 values. But this simplified representation, it covers 99% of the cases. It's a lot easier to work with. It's a lot easier to explain. So I use this one in my code base. So let's see a few of these optics. The first and most important one is the lens, which is it's basically it's a struct. So generic struct with the 2 parameters. And this struct has 2 properties. Those properties are functions. Okay, in Swift, we can handle functions like this because they are first-class citizens, so we can just assign them to properties. The view property takes the root, takes the whole data structure, and returns the part. And the update property takes a new value for the part and the previous version of our data structure and returns the new one. So basically, this is like an encapsulated accessor. We have a get and a set. And we represent this with 2 functions on a type. How can we create a lens? We actually have a way to create them in Swift that is very nice, because we have KeyPaths. We can actually make a lens from a writable KeyPath. And this is a completely generic code. As you can say, I'm returning the lens, and I am just assigning closures to the property using the writable KeyPath. And I can assure you that there is only one way to write this function, really. I'm going to say this a few times during my talk. There is only one way to do this. I would say there is only one sane way, because of course you could put a fatal error somewhere, or you could make a function that does nothing, just returns the root on the second closure there. If you want to do something, okay, the types really guide the implementation. So that's why I say there is only one way to write this. This can be done also because the writable KeyPath is available only on a type that has variable properties. Even if you have immutable types with let properties, this can also be done, but you will not have a writable KeyPath, so you have to provide this function a way to reconstruct the type. But if we use structs, we really don't care. Most of the time, when we use structs, we can actually use variable properties, because even if I mutate a property on a struct, if other parts of my application are referring to the struct, that information is going to be preserved for them. Okay, the good thing about these optics and this representation is that we can add functions to them, methods that are very useful. For example, on the lens, we can add this modify function that takes a transformation of the value and returns a transformation of the root. This is frequently what we want to do. We have this transformation of the value given some event that happened in our application, and we want to transform the data structure. This can be done completely generically. We can add a lot of these things to these optics thanks to their shape. Let's make an example. Let's assume that we have this login page with username, password, and also a couple of flags like this is remember me active flag. Now, we would like to add lenses to this. For example, we would like to add the password lens. A way I like to do this is by adding static functions on the type. So we can actually scope these lenses inside the type instead of using a global function. And we are still passing a writable KeyPath there, but that KeyPath is scoped. The root is fixed on the login page. So we can create the password lens like that. Login page.lens, and we pass the password KeyPath, and because it's scoped, I don't have to say \login page.password. And for example, I'm creating this function here, trim password, that takes a login page and returns a login page. This is the function that we are going always to create, function that takes the data structure and returns a new version. And I'm using the modify method. And to the modify method, I'm just passing this closure, okay, that trims the white space. Another thing that I do, another function that I can add to lenses to make them more useful is the zip function. Zipping lenses means that I can take one, two, or more lenses that share the same root, and basically I can merge together into one single lens that has the same root, but a tuple with all the values. This means basically that this lens will allow us to focus on multiple values at the same time. For example, let's assume that this login page is part of a bigger data structure. And we also have a user session, and what we would like to do, for example, is we are presenting the login page, and we would like to see, we would like to set the username on the text field if the username was stored, and if we have our flag checked. So the players here are the username on the login page, the username the current username that was stored, and the fact that our flag was checked. So we can actually zip these three lenses, the lens on the username, the current username stored in the session, the username on the login page, and on the flag. And then on our restore username function, on the stored username lens, we call modify. The closure that I'm passing to this takes three values and returns three values. The source of these three values doesn't matter. Actually, someone else could write this closure here. Someone else could write this function. I'm just telling you, these are the values, the previous values, and just compute me the next ones. And I'm using this closure to transform my application struct, thanks to this modify method. Another very useful lens that I use, I'm just going to present it because I'm using it later in the presentation, is a lens on a key of a dictionary. On the value associated to the key of a dictionary. So I pass a key, and I get a lens from a dictionary to an optional value. Of course, it's optional, because the key could not be there. Maybe it's not there, or maybe there is nil at that key. This is pretty useful. We will use it later in the presentation. Now, let's move on. Another optic that is called prism. So, if lens is for structs, prism is for enums. Again, struct with two generic types, a match function that takes the root and returns an optional value. Why? Because it matches a particular case of our enum, and the build that is basically the same thing as the case of the enum, takes the value and returns the root in that particular case. this might be a little bit confusing, so let's make a simple example. Assume I have a login state with 4 cases, and 3 of them have an associated type. Now, I would like to add prisms to this, and I can add a prism for every case. There are many ways to add this, and unfortunately, we don't have for enums the KeyPaths that we have for structs. This is something that the Swift lacks. To recreate a similar experience, we can actually create our prism, the definition of our prisms, on the prism type itself. We just constrain the type. When, for example, the root is the login state and the value is a string, we can create a success prism. And as you can see in the build on the bottom, literally I'm just calling the success with the message. In the match, I'm doing a switch, or I could do an if case let, in which if I have the success case, I return the message, otherwise I return nil. This is not something that we can really do in native Swift right now. And if we are able to generate this code automatically for us, for example, with a code generation tool like Sorcery, we get these things for free. Now, for example, let's assume we have a login state, any state. We grab the success prism and we can match, okay, the state with the success prism to get the message. Of course, in this case, it's going to be nil. Now, let's assume we have a different example, a few enums that are actually nested. So an enum for which, in a case, we have another enum and another enum, etc. We, again, would like to compose these prisms, but we need a function to do that. This is the function here. The pipe function, which is a function that takes a bunch of prisms and will basically compose them. If I have a prism from A to B and a prism from B to C, I get a prism from A to C. And again, this is one of those cases where the implementation is very simple because there is only one same way to write that. So this is the example that I was talking about. I have an event enum with a login enum, with a login outcome, etc. And basically what we would like to do is we have an event, and if traversing our structure we get to the failure state, we would like to do something with the message. We, in general, what we can do in this case is to do a pattern match. So with a switch, we pattern match on a bunch of on a path inside our enum. Then we get the message. But if we want to do something on that message, eventually we will need to recreate again the entire structure. And for every case, we have to do this over and over again. We can use prisms and we can compose them. We just need another tool, which is this try modify function. Try modify is similar to modify, takes a transformation on the value, returns a transformation on the root, and basically what it does is it matches the prism. If it gets the value, transform it and rebuilds it. And this is completely generic. We don't need to do a specific pattern match for this. So, provided that we have this, what we can do with this thing, sorry, I have my slides that are a little unmatched. We can add prisms like this by extending the prism time and adding these computer properties, so we can kind of recreate the KeyPath experience. That failure method prism, if you read it, event.prism.login.trylogin.failure. It looks kind of like a KeyPath. And when I want to, for example, transform my event to make my message uppercased, I can use this prism by just using the try modify method. And the idea is that what this is going to do is it will traverse the prism, it will grab the message if it's there, transform with the closure that we passed, and then we rebuild the prism. And then if we have prisms defined for the cases of our enums, we can do something like that that really looks like a KeyPath. Okay, last one. The last one is called Affine, and it kind of looks like a lens in the sense that it has an update function, but it's like a failable lens. It's an optic that will focus onto a part of a data structure, but we allow for that part to not be there. We allow for the data structure to be in a certain state for which that part is not available, basically. So it's like a glorified if, I would say. Two functions, again, preview, not view, but preview, and returns the optional value, but because, again, maybe it's not there, and try update, in which we pass a value in the previous route, and it will return an optional route, because basically what the Affine says is, well, you know, if the route is in the state described by this Affine, well, I will actually update the value. Otherwise, I will leave the route unchanged, and I will tell you that because I return nil there. This is a very, very interesting optic, because if you ever wanted, for example, to operate on a value inside an array, for example, a value at a certain index, or the first value that matches a predicate inside an array, we can actually define an affine for that. This code is exactly that. This affine for first where I pass a predicate. This is an extension on array, by the way. I pass a predicate that takes the element and returns bool, and returns me an affine that will focus on the first value that the affine finds matching a certain predicate. Of course, the preview function will just call the first function on the array. The try update will check if there is an index for that element, and then will mutate the array. We'll remove the element at the index and insert the new element inside. So this affine encapsulates this operation. And I find it, both this and also we can define an affine for a certain index inside an array, very, very useful in a lot of cases. And actually affine really, it kind of generalizes both lens and prism. Because if we think about it, affine is like a failable lens. So if we have a lens, for example, we can turn it into an affine. The preview function will just be the view function, so it will never fail. And the try update function will be the update. So again, it will never fail. But we are just concealing this inside an affine. It's the same for prism, really. We can transform a prism into an affine. Because what we do, now the preview function is exactly like the match function on the prism. And the try update function will be like the build, but will ignore the previous value. Why I'm telling you this? Because if we have a pipe on affine, if we are able to compose more affine together, and if we can turn lenses and prisms into affine, basically means that we can actually compose lenses and prisms. This is an interesting thing, because if we have a data structure that kind of mixes structs and enums, and we want to explore this structure in some way, sometimes it's really hard to do imperatively, just matching and doing ifs and something like that. But because we can lift both lens and prism to affine, and we can pipe affines, we can actually just compose these things all together. So let's see a more complicated example. Let's assume I have an enum that is called transaction state. On the success case, I have a dictionary. The value of the dictionary is a transaction result that has a couple of properties. One of them is outcomes, an array of outcomes. And a transaction outcome as a user and the balance. So I have an instance of this. And what I'm saying is, let's assume that I want to go into the success case, grab a transaction result at a certain key, grab a certain outcome based on a predicate, and on that outcome, I want to act on the balance. Let's assume that I won't double it. Can I do that with these things? Yes, I can actually use these optics very clearly to represent this kind of query on my data structure. I'm going to show it on the next slide, and I'm going to go line by line in the code. So what we're doing is we are creating an affine in which we pipe a bunch of other affines, a bunch of things. Actually, because we can always turn both a lens and a prism to an affine, we can just pass lenses, prisms, and affine to this pipe function. So we have the prism on the success case. We are using this lens on the dictionary at a certain key. Then we are using this optional prism. This is a very particular one. Basically, this encapsulate the optional inside a prism. So it's like removing the optional from the equation. Then I am into the transaction result now. I can point to the outcomes with the lens. The outcomes is an array. So I really want to search for the first, for the first user that matches a certain predicate. And then I get the outcome and I focus on the balance. This entire thing will give me an affine. And on this affine, I can make a preview, so get it, or actually try to update it. And it will handle the reconstruction of the entire data structure. So to recap, functional programming rocks, and really, even if it's just a bit, even if you just use a little bit inside the core of application to describe, business logic, things that have to be very clear and precise, I find it extremely useful. But especially well-defined data structures, are the clear to testable and maintainable code. I read the code, I read the data structure, their description, both structs and enums for represent different cases. For example, if you have a state that can be either an error or a success, you can use an enum. You should use an enum. Unfortunately, a lot of Apple APIs still use the optional error, optional success way. This is bad because you don't have, there is no way you could get two nils or two values, both the success or the error. That thing is better represented with an enum. Either is success or is state. So, well-defined data structure will help you to, write more maintainable code. But optics are just a useful tool to operate on these data structures in a generic way. So for structs and classes, there is the lens. Prisms are for enums. And finally, affine for any kind of optional access. Thank you.